All right, good afternoon, everybody. Thank you for being here on this Monday afternoon for the RAL seminar, and for those online as well. Very pleased to introduce today our speaker who is visiting from New York. He's Emeritus Professor in Earth Science and Engineering at King Abdullah University of Science and Technology in Saudi Arabia. Name's Georgi Stenchikov and goes by Gira as well. So just a little background on Gira before we begin. He goes way back to the Moscow Physical Technical Institute in 1977 when he obtained his PhD studying weak plasma turbulence. So strong background in dynamics. Before that, he obtained a master's in physics and mathematics at the Moscow Physical Technical Institute in 1973. So since then, he's had a long, accomplished career in a variety of research areas, covering topics such as climate modeling. He's contributed to the interpanel UN's climate efforts. He's worked in radiative transfer, environmental science, fluid dynamics, and regional climate issues in the Middle East. And more recently, with his research group at King Abdullah, he worked in areas of scientifically supporting environmental policy adaptation and mitigation, and on measures in Saudi Arabia, such as issues such as climate warming, dust and aerosol impacts and air quality, assessing wind and solar power resources. So a very impressive wide variety of topics. And today he'll present on a somewhat related topic of work on volcanic eruptions and stratospheric incursions of sulfates that can cool the climate. So let's welcome Dr. Georgi Stenchikov to the floor.
Thanks, Chris, for extended introduction, and thanks, RAL, for organizing my visit to NCAR, and Paul for doing this. And thanks everybody for coming. So I will be talking about aerosol impact on climate and climate system, atmospheric processes. It is related to number of effects. I start from geoengineering because it is studies now very active in calculating impact of different type of injections, stratospheric injections, not only, but I will be talking from this point of view. Talk about geoengineering as SRM, and management of solar radiation. But geoengineering requires some experimental support, and it is very limited. At this time, these studies are mostly based on model simulations. The very well-known natural process that mimics what we try to do using man-made injections in the stratosphere, volcanic eruptions. Actually, volcanic eruptions were at some time push the ideas to apply geoengineering. They will explain many processes and explain some side effects. And in this talk, I will be focusing mostly on the initial process, how this injected plume will evolve, and how it depends on parameters of the plume. And for this, I will use two, not recent, two eruptions that I was involved in working with. It is Pinatubo eruption and recent eruption of Hunga. They're quite different. I will explain it in a little while. But they produce strongly different effects. And this will help us to understand what could happen and how we can optimize or so understand the possible dangers of the artificial injections. So I will talk about initial stage of aerosol injections. Pinatubo and Hunga. Pinatubo is the strongest eruption of 20th century and 21st so far. It produced effect slightly higher, so bigger than natural noise, so differently from Hunga, which is very small, but in terms of climate impact. But Hunga is the largest injection of water vapor in the stratosphere. So this never happened previously. It increased the amount of water vapor in the stratosphere by 10%. It was expected that it will produce very strong effects. And understanding the evolution of this injection is very important. And initially, people thought that Hunga will cause warming because water vapor is a greenhouse gas, and if you inject it, you expect some greenhouse effect. So understanding what happens, will enrich our understanding and ability to predict the effects. Recent 15 years are spent in the King Abdullah University of Science and Technology. It was organized in 2009, and I was one of the first faculty there. And this is how this environment look. KAUST, King Abdullah University, abbreviation is KAUST, is at the coast of Red Sea, somewhere here. And it is 100 kilometers north of Jeddah. Jeddah is a big city with international airport. So it is right at the coast, and these are buildings. And my office was in this building, mathematical building. Sunset, this is old Jeddah. These buildings are from Ottoman time, still there. This is director of GFDL, Ramaswamy, that we are at the golf course, not far from KAUST. This is my group, part of my group, and this is Osprey. It is sea eagle. So we have some instruments measuring dust deposition on the island. And we were not the only people, or I don't know, not people, I should say, creatures that visited this island. There was ospreys there, and they destroyed our instruments usually. So that was the problem. But you can play with their chicks. They were there, and so it was very nice. And this is the announcement on the wall of the dormitorium. In KAUST. Usually, as I remember, in my time, it was written something different. It was said, "Don't take girls in the dormitorium." So that was many years ago. But here they worry about women. And this is old railway in Tabuk, in the north of Saudi Arabia. Ottomans built railway that was destroyed during the liberation. But some stations are still there, and one station in Tabuk. This railway went from Damascus to south of Saudi Arabia. So it was pretty. So they will try to reinstall it again, but not quite ready yet. This is flood in campus in 2009. So it rains very seldomly, but if it rains, it rains. So there was 1 meter of water in campus. And this is how coastal plain looks in Saudi Arabia. And it's not empty. There are many animals there. So if you go further to these empty places, you find farmlands, and you find these camels there. Okay, so as I was in this place, so I worked a lot with aerosols. And dust is an important process there. This is strong dust storm in 2012, and we tried to reproduce it. And dust produced pretty strong effect, and it affects solar radiation. Of course, dust is in troposphere and doesn't live very long, but there is always the source of dust. So the optical depth in this area is on the average is 0.3, 0.4. So when first we came to Saudi Arabia, in the night we didn't see the stars because it is different latitude. So we saw maybe the sky is different here. But when after rain, we saw the stars, we understood that it is just optical depth that prevents us to see the stars most of the time. It is not the only aerosol what I dealt with. So this is collapse of World Trade Center in 2001. So we calculated transport of pollutants from this event. It is in published in 2006, 5 years after this event. I also worked with, no, not in this direction. I also worked with forest fires. This is Chisholm fires in Canada in 2001, and they produce plumes that long-lived and affect atmosphere. So recent fires were in Australia, and we discussed that this aerosol could be transported into the stratosphere. But the first my encounter with aerosol impact on climate is related to effects of nuclear war on atmospheric environment. So this study was called nuclear winter, this effect. And in this case, we talked about emission of sooty aerosol into the troposphere. But because of solar heating, this aerosol could be lofted into the stratosphere where it could live much longer and produce long-term cooling effect that was called nuclear winter. If you want, you can call it geoengineering, but it is so negative in this sense. But so this was my first encounter with strong aerosol pollution. And this is leftovers, the team that worked on this in 80s. Brian Toon is around. Richard Turka, Tom Ackerman, Alan Roebuck, and myself. Brian Toon and Alan published paper recently in Oxford Press where they put this picture. And this is my presentation, and this is Carl Sagan on the picture. Interesting. This work in the 80s was done on the first supercomputers. In this first supercomputer, Cray 1 stayed in NCAR. That time I was in Moscow and worked on a much smaller computer that is called BESM-6. And it was 1,000 times weaker than Cray 1. And at that time, we thought that NCAR is such a place where so powerful computer is working. Interestingly, when I walked with my grandson recently to Science Museum in London, not far from Imperial College, I found BESM 6 there. It was working, but it is part of the history now. Okay, geoengineering. So that was suggested many years ago, I think first time in 1977. And there are several possible designs, including some mirrors in the space, in Lagrangian point. But I will be talking about modulation of planetary albedo by injecting aerosols in the stratosphere. Why in the stratosphere? Because aerosols could live there for a long time, and you don't need to push million-ton, like with dust. And hopefully it will not affect people at the surface, but it is probably not completely true. The idea is to inject aerosols like volcanoes do, or aerosol precursors, and let this and support this aerosol layer. And so we, at the first time, we calculated how much it should be injected, and it is a reasonable amount. You can inject this and keep this layer and cool the Earth by 1 degree. But there are multiple side effects related to damping, for example, damping monsoon rains and so acid rains, which is maybe not that important, and change of circulation, what we cannot predict really. That's why this research requires some experimental testing. One of the important part of the technology is how we inject and what we inject, and what will be microphysical behavior of this injected material. Will it deposit immediately? Will it evolve in the stratosphere? So what radiative properties these particles will have, how they will grow. And this is not, so we know these physical processes, but we cannot say that they are well reproduced in the up-to-date models. So it is still a challenge. So before we will go in how we can test this and what we know from real injections, natural experiments, what volcanoes provide. So I have to show the people who first talk about geoengineering. And the first paper, first suggestion belongs to Mikhail Ivanovich Budyka. It was a Russian climatologist. He worked in St. Petersburg. At that time, this city was called Leningrad. And he proposed that he worked with volcanic eruptions, and he said, well, if there will be global warming, and he was one of the people who discovered global warming. So we can put several airplanes and inject sulfate aerosols into the stratosphere. That appears to be not that simple. After that, there were a number of publications. One of them belongs to Taylor, Caldeira, and Guindasamo. And influential paper of Paul Crutzen in 2006 pushed this interest to geoengineering at that time. Paul was well-known atmospheric chemist who received Nobel Prize for ozone hole research. He was director of Max Planck Institute for Chemistry in Mainz. So this were at the beginning, and after then, so we have multiple papers and research in this direction. Now I will talk about volcanic eruptions, what we know about them and how they can help, and what we learn from this. I will be talking about two eruptions, Pinatubo and Hunga, and try to compare them. No, this is the plume from 1991, Pinatubo eruption in Philippines. This is our simulation. We know that volcanoes cause cooling. Small volcanoes cause small cooling, and large volcanoes produce larger cooling. So it was suggested that this delaying of global warming at the beginning of 21st century was caused by a series of small eruptions. I don't believe in this, but so that was seriously discussed. This is observations and so my modeling curve that's showing how Pinatubo cooled the troposphere about 0.7 degrees, and it relaxed in 7 years. This is characteristic time of upper ocean. But this will be forgotten pretty quickly, right? So it's short term. As soon as aerosol disappears, system will reinstate its energy balance. But it is not really right, because volcanoes also cool the ocean. The ocean remembers this change of energy balance much longer. And if we look at ocean heat content, and this black curve, it is effect of volcanic eruptions. So they cool the ocean and decrease ocean heat content. And this is the red curve shows the increase of heat content when all forcings are there. And if we would not include volcanoes, the curve will be here. So volcanoes, so actually volcanic forcing decrease the global warming. And if we talk about global warming, it's not only surface air temperature. So I would say, so ocean heat content is much better characteristic of global warming, because it is a conservative characteristic and it conserves this energy, and atmosphere has very little thermal capacity. So this global warming is offset by volcanoes, and that's why in recent IPCC is seriously discussed how we will include future so volcanic aerosol. So without aerosol, we obviously so overestimate the warming. And yeah, and this cooling, so we see the cooling from volcanic eruptions for decades in subsurface ocean. And if it penetrates below so 1 kilometer, then so it stays there and affects the climate. Okay. When in KAUST, we looked at the impact of Pinatubo on regional climate, and so as well as in fact of dust. And this was tropospheric so setting. We developed the first coupled ocean atmosphere regional system and calculated ocean with 2 kilometer resolution and the atmosphere with 10 kilometer resolution, and calculated impact of Pinatubo on Middle East and impact of dust on the Red Sea. I don't have time to talk about this, but if you have questions, we can discuss. The impact on the Red Sea by volcanic eruption by Pinatubo was very strong. So the ocean on average so was cooled by 0.3 degree at least from my calculations. But Red Sea was cooled by more than 1 degree. And the question is, the point is that Red Sea is very weakly stratified. So if you cool the surface, so the vertical mixing happens up to the bottom. And that causes very strong response. And this mixing caused bleaching of corals in the Red Sea, because this mixing put nutrients from deeper layers up and blooming of algae that prevented solar light to come to corals. And that happened for several years. And there was snowfall in Israel after volcanic eruption. And this is related to dynamic effect and change of circulation. To study evolution of volcanic plume, we also used regional model, at least in what I will be talking today. So here we used regional model to study regional atmospheric effects. But here, to study the evolution of plume, we used regional model WRF-Chem, but we applied it in latitude belt with periodic boundary conditions. In longitude and prescribed boundaries in latitude. And first we applied this model to study Pinatubo, initial stage of Pinatubo. So by Pinatubo, so important. The first, it is eruption that was well observed, and it was strong enough so we see the effect. So when we talk about Hunga, so it also was well observed, but it produced very small impact on climate. And when we try to understand what we should expect, we scale Pinatubo. And that's why, but we have to scale it correctly, so it has sense. That's why it's so important to see what big eruption produce, to see how we can scale it to smaller when we cannot observe the response. So we did calculations in latitude belt. We cannot calculate for many years because the plume will go beyond this computational domain. That's why we calculate for half a year until plume is in sight. What we see here is deposition of ash. Volcanoes inject not only SO₂, or sulfur-containing gases that oxidized and produce sulfate aerosol that is mostly affects climate for long period of time. They also inject solid particles. So they are larger, and at the beginning we thought that they are not very important because they fall down during couple weeks, at least most of them. But it appears they play a very important role as the beginning, and we have to account for them. Volcanoes also inject water vapor. Actually, water vapor, it is the biggest mass of gases what volcanoes inject. And they also could involve a lot of water from troposphere, especially in water-rich environment, water vapor-rich environment. But it depends where the plume is coming. So water could stay, but so I will talk about this, but most of water usually disappears. So in this case, we considered two cases when injection is above tropopause and higher up. So this appears to be important. I told you that Pinatubo was well observed, but still we don't know how, where the plume was injected, at what height. So we know that it was strong explosion and parts of the plume was at 40 kilometers, but where the most of the plume was, we don't know. So that's why we consider two cases. So at 17, 18 kilometers and at 25 kilometers. So this is how ash behaves, ash of different sizes. So small ash stays longer, and so very coarse ash deposits very quickly. And water vapor, in Pinatubo case, most of water vapor was frozen and deposited because it was injected at low altitude. And this is what we learn from Pinatubo. So this is ash cloud. This is average over entire Earth as a function of time and altitude. And you see ash was injected somewhere here, and after then it disappears and falls down. This is SO₄, sulfate aerosol, that was injected and persist at 25 kilometers. And this is SO₂. This is another story, effect of SO₂. SO₂ is also greenhouse gas. And when we inject it, so it also affects atmospheric process. It's not very important for Pinatubo size eruption, but it is important for super eruptions. What I would like to show here, this is a trajectory of center of mass of sulfate cloud, SO₂ cloud, and ash cloud, ash plume. And you see that sulfate and SO₂ have uprising trajectory, right? And ash is going down very, very quickly because it is large particles, they are falling down. But this uprising of plume is caused by heating by ash. Ash is well-absorbing aerosol, and solar radiation heats it strongly. And at the beginning, when we have ash, it lofts the entire plume from altitude where it was injected to higher altitude at 25 kilometers. And if we don't account for this heating, then we lose a lot of material because of mixing at tropopause. So this dotted line shows the trajectory of the plume if you don't have this heating. It is kind of important to compare with Hunga because Hunga didn't have any ash, but it has a lot of water. And it played also an important role in the initial behavior of the plume. And this optical depth that calculated when we injected plume at 17 kilometers, this is observations from SAGE. And this, when we injected the plume at 25 kilometers. And you see, so when we injected at 17 kilometers, so it looks pretty much similar with observations. But if you inject at 25, meteorology there is differently, winds are different, and we have absolutely different story. Without ash, without heating by ash, much less sulfate will be available for building than volcanic cloud. To test ourselves, we formulated reverse problem. There are some observations of volcanic SO₂ and volcanic ash after Pinatubo. But these observations are two-dimensional. So SO2 was observed, so the total column. And for ash, it was observed, so aerosol index that we can recalculate to mass to some extent. So we assumed the injections and the height of the injections is restricted by the height of observed cloud. And we formulated reverse problem. So actually it is least square problem. To reproduce these two-dimensional observations. The problem was that there is non-linearity here because ash affects dynamics, and we have to account for dynamics. And we use iterations to solve this. So this is how functional is formulated. And if we look to the answers, so we solve it for ash and for SO2. And we see that from our calculations, most of the material was injected above the tropopause at 17, 18 kilometers. This is ash, and this is SO2. I'm talking about this because when we scale, so big eruption to small eruption, we somehow should choose right predictors how we will scale. So Pinatubo injected so about 17 million tons of SO2. But from here, we see that significant portion of this SO2 was injected in troposphere and was quickly removed. Only about 12 megaton of SO2 was injected in stratosphere. This is important to compare Pinatubo with Hunga. Okay. So Pinatubo, the example of eruption that released most of material above the tropopause, because it is cold point, water vapor was frozen and removed, and only portion of this SO2 that so we observed remain in stratosphere, so it's less than whole 17 million ton or 20 million ton. So Tonga is quite different eruption. It is shallow underwater eruption, so the depth of eruption about 100 meters. That's why it was able to come up above the ocean surface. You understand that most of the eruptions are at the bottom of ocean. Surface of ocean much bigger than surface of the land, right? And most eruptions are underwater, but they are so deep we don't know about them. And this is unique eruption that came up, and because it went through the water, it took a lot of water up. But all eruptions inject a lot of water. But so to keep water in stratosphere, you have to put this water very high up. Temperature in stratosphere increases with height. That's why if we put this water at above 30 kilometers, so there is much more water will stay in stratosphere. It's what happened with Hunga. So it destroyed this island, but it put 150 million ton of water in stratosphere that stayed there. So it increased the content of water in stratosphere by 10%. Huge amount that caused a lot of concerns. But it injected very little SO2. So from first measurements, it is about 0.5 teragram of SO2, but so our estimates show it might be twice, maybe 1 teragram, but still it is 1 order of magnitude smaller than Pinatubo. If we assume that amount that was injected above the tropopause. And that's why climate effect should be an order of magnitude smaller. So it's what we got with the same type of simulations what we did for Pinatubo. We repeated it for Tonga with water vapor injected. And so in this case, 140 million tons of water stayed in the stratosphere. 0.5 megaton injected SO2 produced optical depths a little bit lower than observed. So we have to scale to get reasonable results. And SO2 was very quickly converted to SO4 much faster than usual. And this is because there was a lot of water available. And plume stabilized. And plume behaved differently than for Pinatubo. If you remember, for Pinatubo, most of material was injected above the tropopause and after then lifted up because of heating by ash. But in this case, the plume was at 40, materials were injected at 40 kilometers, and they fall down. And they fall down because of cooling, radiative cooling. 1 second. Okay, I'm sorry, forgot. And in this case, water vapor plays the role of affects dynamics. It cools the plume, and it falls down. It falls down until 27 kilometers and stabilized at the same altitude as Pinatubo cloud at the end. But trajectory is different, and so what is important? This high plume didn't interact with tropopause. So there were not losses of material to mixing through tropopause. That's why the optical depth per unit injected SO2 a little bit higher for Hunga than for Pinatubo. And this is this trajectory. This is water vapor down. This is temperature, and you see especially good this downfalling trajectory. So we were able to reproduce this trajectory and stabilization of the plume at the right level. This is observations isolines, and observations are shaded. But observations lose this period just because it is condensed plume and not well observed because of sampling error. And horizontal dispersion we also produce pretty reasonably well. Radiative forcing. So everybody thought that water vapor, greenhouse gas should warm atmosphere. But so if you calculate instantaneous radiative forcing, water vapor higher up actually cools the atmosphere because it irradiates directly to space. So to start warming, you have to let stratosphere to cool. If you make this stratospheric temperature adjustment, water vapor begin to warm. So radiative forcing is positive. But effect of water vapor appears to be, radiative effect of water vapor appears to be small. And the reason for this that Hunga injected water vapor too high. above 25 kilometers. So water vapor that increases in stratosphere and affects global warming is in lowermost stratosphere, just above the tropopause. And this water vapor affects climate and affects troposphere. But water vapor higher up, so much less ability to affect troposphere. And that's why this huge 10% increase in water vapor in the stratosphere didn't affect troposphere that much as expected. The strongest effect belongs to aerosol from Hunga that produce forcing that is order of magnitude smaller than Pinatubo. And that's why we expect instead of 0.5 degree cooling, something like 500 degree cooling that is not observable. And this is heating rates in the stratosphere. So aerosols affect heating rates, but much smaller than water vapor. And you see water vapor produce cooling in the water vapor layer, but warming below. Roughly, water vapor layer irradiates up and down. And what irradiates infrared radiation. And what irradiates down, so warms the stratosphere, and the layer itself loses energy. But there's very interesting effect that was difficult to explain. So as I said, radiative forcing, if you calculate radiative forcing, it mostly from aerosol, produce about 0.4, 0.5 watt per meter squared cooling at the top of the atmosphere. Okay? So the warming or cooling within the atmosphere caused by aerosols is very small. But with water vapor, we have opposite effect. The strong effect on stratospheric temperature. But there is very small radiative forcing at the top of the atmosphere. And this is kind of puzzling. So why two so optically active agent produce absolutely different effects? So, and this could be explained by two things. The first, aerosol layer is below water vapor layer. It is in more colder atmosphere. That's why it irradiates less. But more interesting additional consideration is related to how aerosol and water vapor interacts with radiation. Aerosols absorb and irradiate uniformly on the spectrum. So they don't have lines like gases. And optical depth of so the stratospheric aerosol is low. It is optically thin. That's why it absorbs and radiates everywhere, but very little. Okay? But when you integrate, you get relatively large forcing. And if you take gases like water vapor, so they absorb in infrared. They absorb in very narrow wavelength bands, right? But in this narrow bands, they have very high optical depth. So the radiative transport is different than for aerosols. And because water vapor is in troposphere, it doesn't let energy from the surface, radiation from the surface, to reach this stratospheric water vapor layer. So it reaches from the top of the water vapor layer in troposphere at much lower temperature. So water vapor layer in stratosphere intercepts much smaller radiative flux. that's why the difference with what it absorbs and irradiates so big. It compensates the effect at the top of the atmosphere, but it produces strong cooling because it absorbs little and irradiates more. And aerosols absorbs as much as they irradiate. That's why the effect on heating is small. So this example how important to look at spectral characteristic of absorbing material. Gases absorb and affect radiative balance differently than uniformly absorbed gases. And so if you calculate the impact on surface air temperature, then so we got in our calculations something what we expect, about 0.4 Kelvin cooling that caused by Hunga eruption during first time. And how much? Yeah. And about conclusions, to validate the effectiveness of geoengineering, we need some natural experiments, and volcanoes is important source of this information that could support geoengineering research. Volcanic eruptions, Hunga and Pinatubo are quite different, and that's why it's very important examples that we have to consider. The early dispersion, initial stage of dispersion of volcanic plume could affect long-term evolution and should be better understood. And it related how we will inject if we will try to perform geoengineering. So Pinatubo and Hunga are different. I already explained. One injected a lot of SO₂ and another injected a lot of water vapor. And water vapor governs the initial plume dynamics in Hunga case, and aerosols, ash, volcanic ash, define the dynamics for Pinatubo. So in our Hunga simulations, we explicitly resolve the initial trajectory of volcanic cloud, and I think this is important to realistically reproduce the initial stage. Hunga injected probably a little bit more than it was observed. We assume that it is about 1 megaton. No, yeah, and Hunga really produced, more effectively produced optical depths because it was high altitude eruption, and none of material was dispersed through the tropopause. The radiative effects of stratospheric water vapor and sulfate aerosol are opposite. Sulfate aerosol warms the stratosphere and cools the troposphere, and water vapor does exactly opposite. It cools the stratosphere and warms the troposphere. And a small effect of water vapor on tropospheric climate is because it was very high in the stratosphere, and its strong impact on stratospheric temperature. It is because it's spectral absorption. That's what I want to present. Thank you.
All right, thank you for that very fascinating talk. We do have about 4 minutes for a couple questions, so anyone online, feel free to put your questions. Slido, anyone in the room, raise your hand. I'll throw the mic at you. All right.
Yeah, thanks for this talk. I have one question to your development of the water vapor. You showed one graph where it looked like the total amount of stratospheric water vapor, or injected amount, decreased by maybe a factor of 3 over the first 6 months.
Yeah.
Yeah, this one.
This is mass of water vapor in latitude belt. Part of the water went through boundary conditions.
Okay.
So that's it's not whole sphere.
Okay.
So we have lost through the boundaries. But so dynamically it behaved like we expected. So it went down to 27 kilometers and after then stabilizes horizontally. And this is because, so roughly it should go up because there is Brewer-Dobson circulation that brings tracer up. But because water vapor cools the air, so it prevents this vertical motion for 6 months, and after then it takes. So when it dispersed, it began to go up.
Any other questions? So just a quick question. Do we have a good understanding that volcanoes have a pretty consistent set of properties of emissions? And is it really a function of the strength of the volcano, or do volcanoes in different areas of the planet have completely different emissions independent of the strength of the eruption?
No, it depends how you define the strength of the eruption. So eruption by itself is a complex process. And volcanic material so delivered into the stratosphere by eruptive jet, and it characterizes the amount of material, the flux of material at the event. And it lifts materials up. But part of material could be delivered into the stratosphere by co-ingebride, I might be wrong in my pronunciation, convection. So the lava ejected. So how to say, the index how we scale volcanoes. So based on the amount of material that they inject. It is not SO2 that is injected in stratosphere. It is mass of lava that came from this material. It is to some extent connected how much SO2 could be so delivered into the stratosphere. Because part of the SO2 is delivered by convection that happens on this lava. It is warm lava that initiates deep convection. And lava emits SO2. It contains a lot of SO2. And this SO2 is delivered to the stratosphere by co-ingebride convection. And this could be delivered only above the tropopause. Strong jet could deliver it whatever, explosive jet. One volcano could be different than another. This explosivity index may be not exactly what we need to say about climate effect of volcano.
Okay, thank you. We are out of time, but I wanted to mention that Giro will be here between this afternoon, and then he's attending a workshop through Thursday, and he's back for Friday and available to meet with anyone that's interested in discussing research with him. And please do reach out to me if you have any questions on getting in touch with them, or you can meet them in FL3 1013. Anyway, let's thank Jer for excellent talk, and have a good day.